Good evening. Glad you've come to this special place here to look at the dark side of life together with me today, together with Sarah and Feryal. We try to give you a little bit of insight in what we've done in the last 1, 2, 3 years that consumed us quite a bit. Now, the work we are doing is with the Event Horizon Telescope collaboration. This is a big collaboration worldwide, literally around the globe with telescopes and people. We have 250 people who are members of the collaboration, 350 people who have been on the papers. And that picture that you see here is from our last collaboration meeting in sunny Nijmegen last November. Actually, it was sunny. I mean, I told everybody, if you come to Nijmegen in November, you expect the worst. And the weather was fantastic. And that's sort of a theme that seems to be running with us, because when we did our observation, the weather was equally fantastic, which never happened before, actually. There are actually a number of institutions around the world which participated in this Event Horizon Telescope collaboration, but there are many more institutions where people came from. So it's not an exclusive club. Scientists who actually have something to contribute were able to join us and actually just help us do this work. Now, we're looking at the dark side, and if you're an astronomer, you love to look at the dark skies with your eyes, of course. And I can just invite you, if you have ever the chance to go to the southern hemisphere, to look at the dark skies in a desert in Africa or in Chile. You see a Milky Way unlike you've ever seen before, really as if it's painted. And you see these dark regions there. These are not dark holes. I mean, even though they're holes, it's seemingly holes in the Milky Way. These are dust clouds that prevent our view into the Milky Way. But in the very center of the Milky Way, there's a very dark secret, a supermassive black hole that was speculated to be there already in the 70s. And in the last 10, 20 years, we've come to realize there's really something very special in the center of our own Milky Way. So let's zoom into that Milky Way, and we penetrate and look through that dust using near-infrared observations, which were done in this case here by our colleagues at ESO. And you see stars and stars appearing, and then you look really into the very center. And what you see is a movie over 15 years, and you see how the stars actually move in the very center. Once you go very close to the center, stars become agile. You see them actually move from, in these days, it was from one year to the next, you would see something move. Nowadays, actually, you can actually see stars move almost actually within a day. Every day, you'd see a star pass by and change location. That was, in this case, with the gravity instrument at the VLT in Chile. What you see here is the motion of one of the stars in the center of the Milky Way. And it's a perfect ellipse. Exactly what Kepler had predicted for the way that planets should move around the sun. That star moves around something on an ellipse. And from the fact how big that ellipse is and how fast the star moves, you can derive how much gravity is needed to keep that star on its orbit. The faster it goes, the more gravitational attraction you need. This star moves with more than 10,000 kilometers per second around that one location. And just last year, it was swinging by that object in the very center where it was going around. Actually, not in the center. It's actually here in the lower left a corner of it. You can derive how much mass you need to keep it stable. It's 4 million times the mass of the sun. Otherwise, with 10,000 kilometers, you would just, zip out of the galaxy. Just go out into space and never come back. Something very dark and very heavy has to be there in this location. What is it? It was suspected to be a black hole for a long time, and you can actually see something. Black holes are not entirely dark. This is a picture of the Milky Way with radio waves. Okay, this is one of the latest images done with the Meerkat array in South Africa, where you have a beautiful view of the Milky Way, not only with your naked eyes, but also with radio eyes. And that is the pathfinder for the big square kilometer array, a global telescope to come in South Africa. And you see the Milky Way is actually bright. It's radiating radio emission all over the place. And these are dead stars who have exploded and produced radio emission from electrons that were accelerated, most of them. And if you zoom into the very center, which we call the Sagittarius A region, then, and you zoom further and further in, you find in the very, very center of the Milky Way a very tiny, small radio source, where a lot of radio emission comes from a very small region. That was discovered already in 1974, and we've used radio observations for many, many decades to get closer and closer to this object. It would become smaller and smaller. And it turns out that is the point around which all the stars rotate in the very center of our Milky Way. This source has 4 million times the mass of our sun concentrated in a very, very tiny region, a region smaller than the orbit of the Earth around the sun. And of course, the natural suggestion is this is what people have always thought are in the centers of galaxies and power quasars. This is a supermassive black hole. But how do we know? Are we sure it's a supermassive black hole? Could it be something else? Black holes are objects where a lot of mass is concentrated in a tiny, tiny point. Well, it doesn't have to be very tiny. In fact, if you fill our solar system with water, it will actually turn into a black hole, okay? Or even, actually, if you fill the Earth's orbit with water, it's going to be a black hole. If you fill our solar system with air, it will also be a black hole. It just has to be a lot of mass into a relatively small region. And what that means is the gravitational attraction becomes so strong that everything will be attracted that comes too close and would have to escape with faster than the speed of light to escape. And that means nothing ever can escape, because nothing can go faster than speed of light. Okay, that's a fundamental speed limit. In the Netherlands, we always talk about 100, 120, 130, whatever. It changes every day depending on the party you vote for. No, Einstein told you speed of light. That's it. Okay, period. No discussions. And if you get too close to a very heavy mass, the attraction, you would need more than the speed of light, and so nothing can escape. Okay, there's no possibility. Not even light. And so light would also be sucked into a black hole and disappear forever. And that's what you'd like to see. And so, we've been discussing and modeling this source with actually many groups around the world. Feryal has worked on this. We've worked on this when I was young, when I still, didn't have gray hair, 25 years ago. And we realized one thing, that if you go to a certain radio frequency, there was light coming from that black hole, but it would come from very, very close to the event horizon, that region of no return where light would disappear and never come back. And if you then calculate how a black hole would look like if it's surrounded by sort of a fog of radio-emitting gas, then this is something that we published at the time. You see a dark region. You see a dark hole. You call it the shadow of a black hole, because you don't really see the black hole itself, because it hides behind its shadow. You see just the nothingness. You see the darkness of the missing photon. That's what you want to see. That would be a characteristic signature of a black hole. And Feryal will later in the second part of this talk will explain in more detail how this looks like. But that was a clear prediction. If there's a black hole, you should see that shadow. Okay? And that's all you're ever going to see of a black hole if you look very close. Right? Now, it turned out there's another big black hole in our neighborhood. Well, neighborhood is maybe a bit a euphemism, because this thing is 55 million light years away. Okay, and that's a galaxy called M87, and that is 1,000 times further away than the center of our Milky Way. But the expected black hole mass is also a factor 1,000 larger. And so on the sky, that shadow should be roughly the same size as in the center of our Milky Way. And interestingly, that source was already discovered in 1918. Actually, in 1918, we didn't even know these things were galaxies. We didn't know there was anything outside of our own Milky Way. We didn't know about 55 million light years. It was just some fluffy nebula on the sky. That's all what we knew at the time. And then, one of the astronomers realized there's a little streak of light in this nebula. He noticed that and marked this, and that was it. Okay. Today we know this is a plasma beam, shooting out with almost the speed of light from the vicinity of a black hole. And I think, Sarah will talk a bit more about how these things are formed and how they are made. So that's like a finger of God pointing towards where the black hole is, okay, in 1918, around the same time where Einstein had just developed the theory of general relativity, where Schwarzschild a few months later in 1916 described how space-time is bent around a point mass, which later became black holes. They didn't even know about black holes at the time. They described it. Hilbert already described how light was bent around these things. Still didn't know about event horizons, didn't know about black holes, had no clue that an astronomer more or less had already discovered that these things existed. It took 50 years to realize that black holes might be there in space, and 100 years later to actually make an image of it. So I always think that maybe somewhere we astronomers see something out there in space which is weird, but maybe it solves some of the basic fundamental questions of physics, as it was 100 years ago. And so that's the beauty of exploring, of discovering, of having such a marvelous universe where so many things are going on. You never know what is the most exciting physics. You just explore and you keep looking, and you find out at some point. If you zoom in into this source, you look at the radio, actually. What I showed you were optical images. If you look at the radio, it becomes clear that this is a special object, okay? It's filled with a bubble of gas, 240,000 light years of radio radiating bubble, all stuff shooting out from the very center of that galaxy. And that picture was actually taken from the Netherlands with a LOFAR radio telescope. Then you zoom further in, and you see this jet shooting out, and you zoom further in, and the closer you get, it always looks the same, until you reach the smallest scales of images made before we use the Event Horizon Telescope. And then you see this little circle which shows that's the expected size of the shadow of the event horizon. And how big is this? It's about the size of a mustard seed in New York, as seen from Amsterdam. Okay, that's the kind of telescopes you need, a mustard seed in New York. Or you have to be able to read the New York Times. Well, actually, Feryal puts it's actually a bagel on the moon. Okay, so whatever you like. And so, if you want to see this, if you want to see that bagel on the moon and eat it, you have to either fly there, which takes a long time, it's 55 million light years away, or you build a telescope. Resolution is given by the wavelengths you observe and the size. The smaller the wavelengths, the sharper your view. The bigger the telescope, the sharper your view. The wavelength is fixed because we know where the radiation is coming, from the event horizon. That's given. Okay, it's a few millimeters or fraction of a millimeter wavelengths. That size is the wavelength of the light coming from the edge of space and time. But then you know how big the telescope has to be, and it has to be the size of the world. Okay, you need a telescope the size of the world. Okay, so we built one. It's called the Event Horizon Telescope, and in fact, it's not such a novel idea. There was already almost a Nobel Prize for it, for the technology behind it, called interferometry. And that is, you take actually telescopes distributed around the world, and you combine them into a virtual telescope. What you do is you record the radio waves locally at each of these locations where the antennas are, and then you bring them together, what we call the correlators and correlator centers. And we had two of them. One was in Boston at the Haystack Observatory. The other one was in Europe at Bonn at the Max Planck Institute. They bring all the data together. And then in the computer, you recreate an image. You create a virtual telescope in the computer. You look at the object from different perspectives, from different angles. And that gives you the possibility to get structural information about the source and how it looks like. Now, these are some of the telescopes I show you here. None of these telescopes actually have had a long tradition in participating in long baseline interferometry. Some of them actually did, but many of them were actually just coming online, available in the last few years. And that's why we are standing here now and not 10 years ago. You see a telescope in Mexico, in Chile, Hawaii, Arizona. Arizona actually was one of the first ones who ever did this. In Spain, actually, that one in Spain was the very first one to actually do this, looking at the center of the galaxy. And the South Pole. And we send people to all the telescopes for about 10 days to observe together these different sources. We actually staffed them with international teams. So from the Netherlands, I think there were people at every telescope. There was someone from the Netherlands, but they were together with people from Arizona, from Asia, from Germany, from Mexico, and other places. So this is truly a mixed organization and a mixed team. And then you have to wait for good weather, because the short millimeter waves are very sensitive to water vapor. Okay, so you all actually probably have been probed by millimeter waves or submillimeter waves already. That's when you go to the airport, right? You have to stand like this sometimes, okay? You're bombarded by millimeter waves and these, or submillimeter waves. And they actually penetrate your clothes, and so that's why we call them in Germany nude scanners. And that's why they don't show you the picture, right? They only show you an animation because the computer sees you naked. But the radio wave actually is stopped by the water and doesn't penetrate very deep. While normal radio waves, which are much bigger, actually go through you, go through walls. But here, water is a problem, and so if it starts to rain, we can't see the sky anymore. Okay. So normal radio telescopes, we can observe during bad weather. That's why we have good radio astronomy in the Netherlands. Okay. But we don't have millimeter wave radio astronomers or telescopes in the Netherlands. You have to go to dry and high sites in Arizona, in Mexico at 4,000 meters, Chile, 5,000 meter height. Or the South Pole, where it's very cold and dry because it's so cold. Now you have to put there some equipment. These are digital equipment we put at all these telescopes. These are racks here of hard drives, what you see here. Each of them contains 8 hard drives of 6 or 8 terabytes. And so per telescope, we record about half a petabyte of data. And then we put them in big boxes and we fly them out next morning, and then they are combined. Problem is with South Pole, of course, next morning takes 6 months because it takes a long time for the sun to rise. You have an atomic clock at the telescopes to actually synchronize the data afterwards. And that takes a lengthy process, actually a year, sometimes longer than a year, to actually combine this all into this virtual telescope. Now, this is tedious observations. This is the team actually before the observations. Then you observe 10 days and nights, and that's how they look afterwards. The problem, quote unquote, that we budget 10 days because we're expecting bad weather. And in this period in 2017, in April 2017, there was fantastic weather around the world for an entire week. We started observing, and it was like, good weather, let's start going. First day, second day, third day, and we're day and night. And then the fourth day, I see some clouds there, we're really tired. So we declared it bad weather, and we had two days of break, and kept on going again, okay? So this was exceptional. We never had such good weather before, and we didn't have it in 2018, then the year thereafter. In we had, so what do you want to tell me, 5 or 1 minute? Oh, yes, I said 5. Oh, gosh, okay. Okay, good. But some of your colleagues said we can go much longer, actually, because you guys paid so much. Okay. Well, I tell you how images are made. If you measure the connection between 2 telescopes, it's like a string. You actually measure the sound of the image to some degree. You measure, because every image you can compose into waves. Okay? In fact, your JPEG compression algorithm does that. It composes images into waves. Does Fourier transforms. And again, Feryal will talk more about this. And so the longer the string, actually, the higher the pitch of the wave, the higher the tone of the wave. And so you have one measurement, you measure one wave of the image, so to speak. This is a simulation, and you have you add the second string or the third string, and they all combine to give you suddenly then the object will appear in the center of the Milky Way or somewhere else that you're looking at. In this case, it looks like a teapot. Okay, so to the experts among you, we actually can see Russell's teapot after all. Okay, you do this. We spent a year on working on this, getting this image, and then we see this final zoom of the image that we made. Let's enjoy this one more time. This zoom into the Virgo. This is a zoom of a factor 1 billion. Okay, this is one of the biggest zooms in astronomy. 1 billion we zoom into the very center. This is M87, radio image, bubble. See the VLT image of the jet. You see jet, and you zoom in and zoom in. Always looks the same until you reach that. And then you see the ring. And to us, it looked so beautiful because it was exactly as predicted. Okay, that's a special thing. It's just a little, it's a little donut. But actually, to us, it means the world, literally. We spend a lot of time, I rush through, we spend a lot of time to make sure this thing is right internally. We spent, for example, we started with blind teams, 4 different teams making images independently of each other with poorly calibrated data. And always, you see, it didn't look quite as nice in the beginning, okay, when we started. But 4 different teams, again, very internationally composed, all came with different softwares to the same result. And then we actually use simulated data. Okay, you see here various simulated sources, rings and disks and whatever, and different algorithms that we used. And the requirement was that all these algorithms should be reproducing with the same set of parameters, with the correct set of parameters, the images correctly. And so only then we actually combined all the different methods and the parameters that recover all different source structures. In the end, we had 4 observations, 4 nights when we would see that we would have observed, and 4 times we would see exactly the same thing. That convinced us in the end that we did the right thing, because if you have just one person reducing data, you can always make an error. But we really cross-checked each other, and that's the power of a global collaboration, but it's also sometimes very stressful, to be honest. It can be very, very stressful to work together like this. What do we do in the future? Just to round up, we need more telescopes. The world is not enough, and Africa is missing. And we don't have a single telescope in Africa. So we're trying. People are trying to look at different locations, and we in the Netherlands here, in particular, trying to actually get a telescope into Namibia, onto the Gamsberg mountain. There's a telescope in Chile which we can have. We can put it there. So that's one of the next things we want. It's not so easy as here in this PowerPoint animation. But we also want to do it together with people in Africa. And so we also want to do together with, we have an outreach program, for example. What you see here on the right side is actually a planetarium that in the Netherlands goes to all the schools. So at least if you have children, there's a 50% chance your child has been in one of these already. And we've taken this to schools in Namibia to just tell them about the sky. Well, it turns out they know the sky very well, but what they were struck by was the Earth, and to see how much water was in there. And so wherever you go to a different location, you change perspective. And it's important to use the entire world to find out how the world really looks like. And if you're there in Namibia, enjoy the night sky. It's just awesome. Thank you.
Hello. So I will pick up from where Heino left off and bring you back to the image. This image, why does it have the characteristics that it has? Why does it look like a donut that somebody frosted haphazardly? Why is there more frosting on one side than on the other? And more importantly, what does it tell us about Einstein's theory of general relativity? I hope you had the black hole cocktails. I understand it makes general relativity so much more understandable. So please, if you're taking orders, now is the time. What I would like to start with is, you've heard the story of how we've put the array together, how it took more than a decade of both theoretical work and experimental work getting the telescopes ready. And at the end, we ended up with this image. And as I said, it's brighter on one side, it has a hole in the center. And we were extremely excited when we got this image. We were hoping this is what we would get, but we weren't sure. And during the time between seeing the image for the first time and preparing our results for publication in order to be able to share it with our science colleagues and you, we were so excited, sleepless. And at the end, we really got an amazing, amazing response. We were humbled, we were excited, we were very happy with all the attention that we got. But I have to say, I mean, yes, the front pages of newspapers was wonderful, but what was so much more fun was the memes. And I just want to share with you my favorite. I mean, among so many creative things, Homer eating the donuts, especially since we said it's the size of a donut on the moon so many times. It was absolutely amazing. Okay, joking aside, what does it tell us about general relativity? What do we learn from this image? What do we know about physics and our universe more than what we did before we were able to do this experiment? So, what I want to start with is showing you, Heino already alluded to this really nicely, that we had multiple imaging teams, we had different algorithms, we had data that we created where we knew the parameters and we asked ourselves, are we getting it back? So in case you think, in the second part of my talk, when I talk about general relativity and why the hole in the center has to be there, why we expected it, why our simulations show it, in case you think that there is anything in our algorithms, in our analyses, that put the hole there, I want your mind to be at rest, that we don't. So I want to show you with a little animation of what it means to interpret the data. On the right here is the real data. This is what we collected. So these are different pairs of telescopes that gave us these different notes of the image that Heino was alluding to. If I understand that Science and Cocktails audience is definitely above an average audience, so maybe some of you know this concept of a Fourier transform. So we basically look at the various components of that image, and we plot it. This is the actual data. So let's say that we were trying to fit this data with something that looked like the blob on the left side. Full in the middle, right? Something like this. This is for scale. This is the size. This is micro-arc seconds. Okay? You see that the green line does a terrible job of fitting those data. Okay? What can I do to it to change it? I can make it a little bit bigger. Okay, we are on the right track. At least we can get this part right. But really, this part is really terrible, right? There is this ringing that is not describing the data at all. It's not until we introduce a hole in the center of the image that we come anywhere near being able to describe these data. This is what we call the robust features of the data. It requires the existence of a hole in the middle. It's not quite there, as you can see, and I can do a little bit better, even at this level. And I can just blur it a little bit to the size that our telescopes are able to resolve, the scales that our telescopes are able to resolve. And then we get, is this the best image? No. But does it get the robust features of the data right? Yes. So what I'm saying is that something like a donut has to be there. And this is what excited us. A black hole in the right wavelength, with the right conditions, has to reveal this shadow at the center. Okay, why is that? So this is our little detour into Einstein's theory of gravity, which we call general relativity. It's actually fairly simple. It basically says that space-time is a fabric, and if there is no matter around, nothing massive like me or our sun or a black hole, that fabric is straight. Okay? So what I'm going to do is shoot light rays through it, and light rays travel in straight paths. That's what physics tell us. So if my fabric is straight, light rays are going to travel in straight paths. And then what I'm going to do is throw a black hole in there, and you'll see what happens. Okay? So as promised, I've drawn a grid up there for you, so you're able to follow the light rays. But now, the black hole creates a warp in that space-time that is so deep. In fact, we call it an infinity. This is the even light can't escape part. What happens is that when we play it again, you will see further away light paths, ones that are farther away from the black hole, are still feeling a little bit of a deflection. We call this, they're changing their paths a little deflection. But look at these ones. They're completely trapped in that center. They can't get out. This is a characteristic of this theory of gravity. If you push it to the extreme, where there is a mass in a very compact area, it will warp the space-time to a point where it traps light at the center. Okay? That's why if there is light around a black hole, some of it we will be able to see. The ones that happen to be a little bit farther away, they will still get to us, but the center of the image is going to be missing. Now, when we talk about black hole environments, it's not just a flat fabric. There is actually gas swirling around it. The reasons black holes grow in the first place, and this is something Sarah is going to talk a little bit more about after me, is because they are able to consume gas from nearby stars and clouds. So what happens? They catch some gas. This gas starts swirling around the black hole, slowly makes its way in. And during that journey, it heats up. It gets really hot. It has other properties like magnetic fields and all sorts of fun stuff. So what we try to do is build as faithful physical models of the black hole environment as possible. Here what you see is this black hole at the center. There is this gas around it. The colors show different densities of gas, different temperatures of gas. And we use big computers in order to not just follow the motion of the gas and its properties, but the light that it emits, and then following rules of general relativity, does that light get to me? How does it look? If I made an image, what would it be like? We've done this for many years. We started it in the late 90s, making these models as physical as possible of black hole environments. But as time improved, of course, our computers improved. And at some point, we started being able to use even new technologies in order to make our predictions even better, even more precise. What I'm going to show you is something we started at the University of Arizona about 10 years ago. And what we said is that, okay, we are able to solve Einstein's equations on normal computers, what we call CPUs. But there's actually a better, faster, cheaper way of doing it. And those are called GPUs, graphics processor units. And you might think, what are they? Actually, you all have one. Take out your cell phone. There is a GPU on there. It's the graphics rendering that we rely on all the time. Of course, normal graphics rendering doesn't solve Einstein's equations. We do. So we kind of hacked it, and we were able to do it much faster. We were able to make movies of black hole environments instead of just stills. So what I'm going to show you is not a GPU and what a simulation looks like. Instead, I'm going to show you a colleague of mine, C.K. Chun is his name, at the University of Arizona, running a simulation in real time using a device called Leap Motion. Okay? So here we go. This is the leap motion. He's going to control his own computer and the GPU on it, and the code will run in real time, solving the field equations. So he's initializing it. So we call it computer gaming on steroids because obviously we're having fun with this, right? So he's controlling the simulation with 1 million light rays, and he's running it forward and backward in time. And what you will see is that when we use this technology in conjunction with the gas simulations, we can also follow exactly the missing light, what gets trapped by the black hole, and we are able to look at it in many, many different ways, for different size black holes, different conditions, different temperatures, and all sorts of wonderful virtual experiments we are able to do around black holes. So we implemented this technology in order to understand what we're looking at a little bit better. What do we expect? So one of the things that Heino talked about is that we perform our experiment in millimeter waves, right? There's something special about being able to see down to the event horizon and being able to reveal that shadow. Why is that? Why can't we do it in centimeters? Why can't we do it in X-rays? There's a whole electromagnetic spectrum. Why did we pick the millimeter wavelength? It's the Goldilocks story. I don't know if you're familiar with it. Americans grow up hearing about the not too much, not too little, just right. So millimeter waves turn out to be the Goldilocks for our experiment. Because if we go to even longer wavelengths, there is too much light, to the point that it obscures our view to the horizon. So it's there, but it's basically, it looks like this torus. But now watch what will happen when I crank down the wavelength. So I start going from centimeters to millimeter waves. That plasma will disappear, that obscuring a material will disappear, and we're going to be left with this crescent that we have in the middle, this ring-like structure. And now I'm running the movie forward because black hole environments are dynamic. The gas doesn't just sit still, it actually moves around. So one of the things we wanted to understand, for example, with all these suite of simulations is there going to be a change from day to day, month to month when we look at this source? Is the structure of it going to change? Or are we dominated by the gravity so strongly that no matter what happens to the gas, are we always going to be able to see the hole at the center and test Einstein's theory with it? So this is just actually an extension. This is something near and dear to my heart because I was a graduate student when I started working on it. This is one of my first predictions of how the image size would look as a function of frequency, showing that right around the millimeter wavelength for our galactic center, we would be able to perform this experiment. And obviously, we've come a long way since 2000. The simulations that I showed you are from the last few years. So we didn't stop there. We have a global collaboration. A lot of us developed these wonderful tools, many different techniques, many different conditions, and we really wanted to know what is it that we can learn about black holes by getting this image. One thing that we learned is that for the right conditions, as I said, right observing wavelength, right type of black hole, we will always have the shadow at the center. In some, the rings are a little bit fatter. In some, they're a little bit thinner. In some, they swirl around faster, as you can see, because we also don't know exactly how we look at black holes. Are we in the line of sight of the jet? Are we looking perpendicular to it? So all these unknowns, we are able to do computer experiments to be ready for all the possibilities. One other thing, coming back to this half-frosted donut, as you see, some of them most of them, in fact, are a little bit brighter on one side than the other. That is an effect called the Doppler shift. And what that is that light or sound waves, all sorts of waves, moving towards us, come to us at a slightly higher frequency and they're a little bit louder, a little bit brighter. And the part that is moving away from us, just like an ambulance as it's receding from you, it sounds a little bit lower pitch and a little bit dimmer as a sound. The same thing happens with light. Because the gas is swirling around the black hole, the part that it happens to be coming towards us looks brighter, and the part that's swirling away from us looks a little bit dimmer. That's what gives that. That's why it's not a perfect ring, but it's this asymmetric structure. So this is the simulation library we built as a collaboration. This is 100 among the truly thousands of cases that we were able to simulate. What did we learn? Well, we actually, even with this first image, were able to make strides towards asking, was Einstein right? And when I say was Einstein right, I really mean the theory, because Einstein did not do anything about black holes. Einstein hated black holes. His entire life, he was resistant to the idea that his beautiful mathematical theory could produce something as crass as a singularity, that fabric of space-time that was infinite. And he actually never worked on black holes and never, ever wanted to accept their reality. It was all sorts of other people, especially starting in the 70s, that developed this concept that if there are black holes in the universe, which we're going to hear the story in a little bit about how we started thinking there are black holes in the universe, what their properties should be. We took a bite of that as well, of that endeavor as well, and we wrote a series of papers. This is my colleagues and I at the University of Arizona, and we said, okay, let's say that we have a black hole image. What will it actually tell us about whether Einstein was right or wrong? We said three things. One, from an image, we can tell the mass of the black hole that produced it, independent of the spin or orientation of that black hole, how it's oriented in the sky. The second thing we said is, if we know the mass through other means, then we can actually test whether the size that is predicted is correct. And the third thing we said is, general relativity makes this one more assertion that a black hole is described by only two quantities, mass and spin, and there is nothing else that describes an astrophysical black hole. We said, can we find ways of testing that? What if there is a third quantity? Can we tell the difference in an image? So very quickly, I want to show you how we use this image to answer two of these questions. Measuring the mass of the black hole, obviously we did something a little bit more sophisticated than this, but effectively what we did is say, okay, here's a circle. What is the size of that circle? And using our predictions, what is the mass that it gives? Okay? The diameter of the circle turned out to be 42 microarc seconds in these funny units that are too small to even think about. The important thing is it said the black hole mass has to be 6.5 billion times the mass of our sun. Heino already talked about this. There are things we know about the black hole in M87. We know that there are stars orbiting around it. It's not as clear a view as what we get from our own galactic center black hole, Sagittarius A star, where we can see individual stars. Here we can see stars orbiting in general, but that's good enough. From the motion of those stars, the mass that was predicted was 6.5 billion solar masses. So two completely different approaches. One is looking at stars that are orbiting the black hole a large distance away. The other one was, what is the size of the hole that is left in an image? And they wonderfully agreed. When it comes to our own galactic center black hole, we'll be able to do this experiment even better because of the precision of the measurements. The last thing is that we said a black hole casts a shadow on its surroundings. General relativity has a wonderful prediction. That shadow has to be a circle. That comes from this fact that a black hole has two quantities. If it had a third quantity, if general relativity wasn't complete, if it was wrong in some way, the equations were wrong, our understanding was wrong, then you could take that circle and turn it into something that is quite a bit different than that. You could, in principle, make it any shape you wanted, depending on your extension of general relativity. But the fun thing is, even a small deviation in the theory would cause your image to deviate from a circle. Believe it or not, we already were able to put an upper limit on this. So using our image, we said there is no deviation from a circular shape to more than 10%. Can we do better than this? For sure we can. We're going to keep working on it with more data, with our galactic center black hole, and maybe one day on more black holes. So this is going to keep on getting better and better, but what I wanted to share with you is that while we loved the image and we loved the fact that the experiment worked, we were actually able to do a lot of quantitative tests even with this first one, and it's going to improve from here. With that, I want to turn it over to Sera Markoff, who's going to tell you about the role black holes play, the bigger role black holes play in our universe.
Oh. All right, hi everyone. I know I'm the last thing between you and the cocktails and the music. This is actually kind of special for me, I have to say. So first of all, I love the Paradiso. I come here a lot, but actually Marco from the next band is one of my best and closest friends. And this is the first time that we've actually been able to perform together. So I want to say that thanks to Science and Cocktails for bringing science and music together. It's really a fantastic combination. Sorry, my voice is a little hinky today. So what I want to talk about in this last talk is really taking a step back from what Feryal and Heino have spoken about and putting these results a little bit into the greater context of what does this evil donut shape actually mean for helping to better understand the universe. And I think before we get really into the science, it's useful to think a little bit about the historical context. Heino alluded to this a bit, but we live in a really special time. And of course, everyone who has ever lived thinks that they live in a special time, but I think we really do. If you think about, human consciousness for the last whatever million years developing, just in the last century have we been able to actually even think of the questions or try to be able to answer them. We just didn't have the tools until a century ago. And so when Einstein developed his theory of general relativity, he was able to basically say that this thing that we thought was a normal force, gravity, is actually a bizarre byproduct of the warping of space-time, this four-dimensional fabric that we couldn't really see or touch, but we're embedded in around very massive objects. And so what happens is stuff moves in this warped space-time, and we interpret that motion as a force. And that's a real paradigm change. That was a huge shift from the Newtonian idea. And so basically, a lot of exotic things came out of this, like black holes. And of course, Einstein, as Feryal said, really didn't like this idea. And so for a long time, people did think that, for about 50 years, they really didn't think they were real. But things started to change in the early 60s. And actually, it was a Dutch guy. His name is Martin Schmidt. He was working in the US, though, in my country. But anyway, and he was looking at this is a historical image. He was looking at this fuzzy thing that kind of looked like a star. And he took the first spectrum of this, and a spectrum that tells you that this thing has a redshift, and you can measure it, and it's very far away. In fact, it's in another distant galaxy. So this was the beginning of opening up the universe to humanity, this concept. It had to be, since it was so far away, not a star, but about trillions of times more luminous than our star, the sun. And so people started to understand that really the only thing that could power something this bright would be a supermassive black hole. And then the idea really started to take off. I mean, it was big news at the time. He was on the cover of Time magazine in 1963 for this. And so then the hunt was on to try to find a real astrophysical black hole. But I mean, now we really do live in an even more special time, because just in the last 5 years, you know, humanity, again, we've looked at the stars for millions of years, wondered about them. Now, just since 2015, we're able to actually look at the stuff between the stars, right? This fabric of space-time that's holding everything together, basically. And so we saw the merger of two black holes, and these ripples in space-time crossed the Earth and basically shook us. And then 6 months ago, it's hard to believe, but it was exactly 6 months ago, basically, we revealed the first picture, and we're looking down the mouth of a supermassive black hole that's basically the size of our solar system, right? And so this is really a crazy kind of idea. And what it's done is that we're now able to look at light, and that's coming from material, but we're also able to look at this embedded, space-time, and actually where these two meet, it's a very complicated thing, because matter influences the bending of space-time, and matter also influences the light, and trying to understand how this all comes together is a hard problem. And so black holes make basically the ultimate test lab for us. This is what we want to be able to understand, and it has a lot of implications for other things. But before we go into that, it's important to think a little bit about dispelling some myths about black holes. Now, black holes, you always hear there's this cognitive dissonance, right? That light can't escape, nothing ever comes out, what goes in never comes out. It's so deep in our consciousness, they use this in advertising now. And so you can see from cat litter, I was quite flattered. I won't go into the details of directs, but I just found that on the internet recently, that they've been using our image for a lot of different things. And I think that if you, this is real, if you think about, how can something, as you hear us as scientists say that these are the most powerful batteries in the universe, and we're able to change their surroundings. How can this happen if nothing escapes? And so it's important to think about the fact that not everything that falls into the black hole is actually going to escape. And in fact, gravity can impart energy in a sense. So the same way that I can drop a ball, if I'm holding a ball in my hand, it has gravitational potential energy from the field of the Earth. If I drop it, it starts to move and it becomes energized. And it's not that that energy comes out of nowhere, it's all conserved, but basically it's a conversion of different kinds of energy. And that's exactly what black holes do, is when they pull material towards them, basically they're able to energize the material, and then it starts to convert that and channel it into other forms that turn out to be very important for the development of structure in the universe. Now, you're maybe familiar, this is actually the artist's impression from 1975 of the Voyager, but if you watch sci-fi like I do, you've heard of gravitational assists or slingshots. But basically, this is Voyager launched from Earth. It whipped around Jupiter, gained energy from its gravitational field so that it could come out to go out by Saturn. So this is a known thing to you intuitively, that you can use gravity to energize. And that's exactly what a black hole is basically doing. So when material is falling onto a black hole, it's a process that we call accretion, and it spirals into the black hole. And then, as Feryal is mentioning, this is magnetized material, and so actually the magnetic fields get amplified, and this is going to be an artist's impression now, but basically you get these launching of these magnificent structures called jets, and I'll show you some real pictures in a second, and these are extremely powerful, but also, and one of the other things that's interesting is that this spin or this motion is another conserved quantity in physics, and it can actually impart spin onto the black hole. So the black hole can act like a cosmic battery and hold that spin energy, which can be tapped, for instance, by these jets, and even give it a boost. But there's other stuff that comes out, these are not coming out of the event horizon, but being launched very close to the event horizon. And there's also things like winds, and light and particles. So this is the complicated system that's around the black holes that we're looking at with the Event Horizon Telescope. And we have to try to understand this in order to understand the context of the image that we're looking at and what it all means. Now, this is an extremely efficient process. So basically, when you think about the conversion efficiency of this mass fuel into these other forms, it's almost 100 times better than the nuclear fusion that fuels that's the next best thing in the universe, and it's fueling our sun. So when this is happening, it's the most powerful force in the universe, basically, and I'm going to show you causes kind of a lot of damage. The other thing to note is that all these different scales means that, first of all, the Event Horizon Telescope, as Feryal said, is really looking at this tiny place down near the black hole. But if we want to understand the effects of the black hole and link what we're learning about the energy release, we basically need to look at the larger scales. And so first of all, we need to look with other types of telescopes that are tuned to look at the large scale, not the small scale. But also, when light comes out at different types of scales, the frequency of the light, basically you can think of it as the color essentially, is determined by the size scale and the process. And so the fact that this is a bunch of different processes and multi-scale means that by definition, what's happening around a black hole is going to be multi-wavelength as well. And so for that, we need to look in other bands. And so what I want to do is give you a picture of the effects that black holes can have on their environment. Now, this is an image, a visible image, but with much better eyes than ours. It's the Hubble Space Telescope. And what you're looking at is a cluster of galaxies. This is the largest gravitationally bound structure in the universe. And all these little dots are galaxies. They're not stars. And it's all held together by gravity. And here's a really big whopping galaxy in the center, Hercules A. Now, we think that every galaxy has its own black hole in the center. So how do we gauge the effect of the black hole on the environment? Well, we can't do it just with the optical alone. And these jets that I was showing you, they're magnetized plasma. So that means that they emit in a kind of light that's called synchrotron, and it basically is very bright in the radio. Now, Event Horizon Telescope is a little bit shorter wavelength than radio. It's the millimeter, but it's the same basic idea with arrays. And so if we now look at this in the radio bands, we're going to see something completely different. Now, these are the jets that I was talking about, but you have to realize the black hole is tiny. These things are 1 billion times bigger than the black hole that creates them. How does that work? How do they stay so straight? They're about 800,000 light years across. And you can imagine that these things can do a lot of damage, and they're extremely powerful. Now, to get another sense of what happens, in the environment, we can gauge this better by using the X-rays. The X-rays trace extremely hot gas that's basically hundreds of millions of times hotter than the deep cold of space. And all that energy had to come from somewhere. So now, and by the way, I should mention, this blue isn't real. The colors, when you're talking about radio waves or X-rays, we can't see these with our eyes, so we use a false color. So I hate to disappoint, but the evil donut doesn't have to be red. It could be pink, it could be green. It's just, we have different conventions. So in this case, X-ray gas is going to be pink. And what you see is there's a huge amount of matter that's trapped in the gravitational field between all of these different galaxies, and it's basically being heated up by the action of the black holes and by their mergers and all the dynamics of this region. And just like a balloon, so this hot gas has to be pushed out of the way in order for these jets to blow up and expand. It's a little bit hard to see here, but what we can do is we can use the temperature of this gas to understand its pressure, and we can figure out how much energy, just like when you blow a balloon, you have to do work. You can figure out how much energy the black hole had to put into the system to blow this up, and it's about 10 billion supernova. Okay, so just think, one black hole, one galaxy, you get these enormous structures, and you're inflating this, and you're dumping all that energy far, far away from the black hole. So I like to use a very Amsterdam analogy here with a communist, proudly communist city, and my institute, the Anton Pannekoek Institute. He was a good friend of Lenin. Okay, black holes are the ultimate socialists of the universe because they're redistributing the wealth. And it's important to think about this because, I also like comic books, but basically, if you imagine that what's happening, and I'll show a movie in a second, but just to explain, right after the Big Bang, there was basically already the structures, the sort of seeds of the current structure of the universe density, overdensities, and underdensities. And then from that moment on, as the universe was expanding, the only force that was operating for a while was gravity. And so the rich got richer and the poor got poorer. And so this filamentary structure developed where basically the regions that were overdense kept pulling more and more material, and that's where these clusters of galaxies and galaxies form. And then there's these empty regions which become poorer and poorer of mass. And the only thing fighting against that is the black hole, basically, at the very largest scales. And so people started to understand this, and when they first ran their simulations, so what you're going to see here is this is a cosmological simulation. You're running forward in time, and the structure is collapsing, things are merging. You can see the dynamics in here. These things take years of computer time. They're extremely computationally expensive. But then basically, in these galaxies and clusters is where the black holes are forming, and you start to see in color explosions. And these explosions come from star formation, from supernova, but also from the actions of the black holes. And if we don't include this in our calculations, we actually don't get the correct distribution of matter in the universe. So black holes are the ultimate players. They have an extremely important impact on the largest scales of the universe. And if we want to understand this, we have to understand the root of the problem. And that's where the Event Horizon Telescope has really come back in. So coming back down now, sort of towards our observations, this is the M87 galaxy that we looked at. You've seen some pictures from Heino and Feryal already. This is not to scale, of course, but there's this supermassive black hole that we know is launching the jets. So M87 has these jets. And also, these jets are visible in all the different wave bands, so across the electromagnetic spectrum, from radio, optical, to X-ray. And so if we want to understand the impact of these jets, if we want to understand how they're launched, we need to tie the regions near the black hole to these larger scales, and we have to understand the light that's being created from them. And that's how we start to put this together to do complicated modeling. So for that, along with the complexities that Heino was describing in terms of having all these different stations and all the weather that we had to deal with, we also did a crazy Sudoku of coordinating our observations with space and ground missions. That's part of what I did for the collaboration. And what turns out is that we had amazing luck both with weather but also with coverage. And so now we're starting to try to put this all together to constrain the types of theoretical models that Feryal was also showing. And so this is actually not a black hole. This is a sun. You might recognize it. But you can see that there's turbulent cells. We know that the sun is basically magnetized plasma as well and is bubbling, and that turbulence is helping amplify, and you get dynamos. We think something very similar is happening in the accretion flow around a black hole. And so in our computer simulations, we take a sort of magnetized plasma like this as an initial condition. We wrap it around the black hole, and then with full general relativity and with what we call magnetohydrodynamics, we let this thing run, and we, from first principles, try to model these big jets. And the technology of using GPUs that Feryal mentioned is also very important for this, because these simulations take forever, basically. And if you can put this on a GPU, it can run, hundreds of thousands of times faster. So this is just some work from my group, but what you're seeing is the donut of material, basically, and then on tiny scales, this is in log scale, but we're basically launching from the same turbulent magnetic fields that we generate in situ, jets that are, this is on the scale of hundreds of thousands of times the size of the black hole. So we're able to finally, in a computer, capture the scales of the system, but the problem is that we don't actually understand exactly how the light is produced yet. And that's one of the bigger problems, and that's where some of the ambiguity comes in. We can do different types of these simulations with different initial conditions, and we'll get jets. We don't know which one's the right jet. And while that didn't affect our observations for 2017, because we were very lucky that it was dominated by the gravitational light bending, so basically we could have a lot of different scenarios, and all those pictures that Feryal showed of our simulations were various different types of initial conditions. We now can basically run these things and forward, but we need the multi-wavelength information to basically put this all together into a consistent picture. So one thing that's important to note is that M87 is in this active state when it has these jets, but black holes are not always active. So they go through these life cycles that last on the order of 100 million years or so. And most of the time, black holes are actually dormant or quiescent, and they don't really do much of anything. And the other target for the Event Horizon Telescope, which Heino was mentioning as well, the Sagittarius A star in the center of our galaxy, is a very quiescent, it's actually the kind of most pathetic excuse for a black hole we know, but it's our black hole. And it's close. So we can see it. We wouldn't be able to study something like this if it were further away. But this is important because we know that millions of years ago, Sagittarius star did look like this. It had this life cycle, and the question is, what would that mean for our galaxy, for life on Earth or on other planets? It's something that people are starting to think about now in the field, and it's a very interesting question. And so part of what we're trying to do by having these are our only targets that we can see the event horizon for right now using the array as it is on Earth, is try to understand the differences. This is, by the way, an X-ray image. We're not seeing the black hole. This is on very large scales, but it's showing you sort of the outer material that's basically coming into the black hole, which is something we can't see for M87, but we don't see these big jets in Sagittarius star, and that's a very big question. So we're trying to compare these two, but we're also going to try to understand what would happen to Sagittarius star and how did it look at the time when it was more active. And it's interesting because just to think, I mean, I read a lot of sci-fi. I mean, you're going to see this from my talk, comic book stuff and sci-fi, but there is another source that we're looking at, several other black hole sources with Event Horizon Telescope that are what we call non-horizon sources. So these are black holes that have powerful jets, but we can't see the black hole the way we can with these other two, but we can see very close down into the structures that launch the jet, and that's also pretty important as well. Now this source is cool because this is now an image, this is grayscale of course, radio and X-ray, and a combined color image. The radio jet is very smooth, but in the X-ray you see these little bumps here, and what that means is that the gas in jet is hitting stuff, and it's getting piled up, and it's shocking and giving off light. These knots we think are high-mass star systems. So these are solar systems, other people's solar systems maybe, that are in the path of these jets. And so you have to ask yourself, what can the effect be of this overall? And I think what's important to remember is, of course, you don't want to get too paranoid, but we're in this little planet floating in this little solar system in this relatively moderate galaxy, but there's a lot of stuff that affects us from the cosmos, and it's important to understand also if we want to understand how life forms on other planets and these effects. And it's interesting, this was from a paper some years ago, but if you look at these extinction cycles on Earth, well, we already think one is pretty surely from a meteor, but now people are starting to talk about gamma ray burst, and what a gamma ray burst is an explosive astrophysical event, but it's thought to be the heralding often of the birth of a black hole. Okay? So nearby events, the creation, the formation of black holes, whether or not the jets are on, this can actually affect in potential life. And I think it's a kind of interesting question as well. And it's also good to remember that we wouldn't be here if there hadn't been these life cycles of formations of black holes somewhere nearby to also create the elements, star formation, heavy elements come. We're starting to learn that all of this is coming from these types of cosmic explosions. So coming almost to the end here, so we have, basically it's not the end for EHT, it's just the beginning. We've only really shown one type of result at the moment, and we have a lot more coming. So we have polarization images, that means we're going to actually look at the orientation of the magnetic fields. That's a big constraint for our models. We're going to look at Sagittarius A star, more complicated and more variable than M87, so that's why it's taking longer, but it's coming. We have all of these non-horizon sources, Sen A is the one I was showing the jets from, that we're going to be looking at, as well as 2018 data, though as Heino mentioned, the weather wasn't quite as good, but we're still working on that. All the multi-wavelength data we have to analyze and put together with what we saw near the black holes. Lots and lots of modeling and interpretation. And then, of course, the future is we have a new run coming in this March and April, so we'll be pretty busy. We're gearing up for that. And the next generation, where we want to start going from still life, shots to actually making movies, and we need higher precision. And for that, we need more array elements. So we're going to be expanding the array, possibly including the African telescope that Heino was mentioning, but there's other ones as well. And as well as maybe going to space and space VLBI and having orbiting satellites that can basically increase the precision. So I think the summary is pretty clear, and I'll leave it at that, and we open up for questions. Thank you.